And so Chen got her PhD in 2017 with Wayne Hu at the University of Chicago, and she's worked a lot on the CMB, in particular on compensated isocurvature perturbations and on CMB constraints on reionization, which she'll be telling us about today. And since 2017, she's been a postdoc at JPL, and she's she's also been involved in WFIRST and SphereX and on constraints from the bispectrum. And so, yeah, so I think you can take it away, Chen.
Oh, thank you so much, Alex. Can you guys hear me all right? Yeah, okay, beautiful. Yeah, thanks so much for inviting me to this to visit virtually University of Waterloo to give this talk. I'm really happy to be here and hope I can meet you guys all in person one day when all of this is over. So yeah, today I'll be talking to you first about the reionization effective likelihood from Planck legacy data. So this is a code called RELIKE. This is the effective likelihood code. There is a GitHub available as well that I've put up here. And this is from a recent paper that was published in PRD just in September in collaboration with Professor Wayne Hu at University of Chicago. So let me go ahead and let's see. Okay, good. Yeah, so I'll start by just giving you a bit of background on why it's important to study reionization for cosmology and also various different fields, and in particular the technique we use called principal component that really allows us to compress this legacy Planck data that we have, which is the best measurement that we have so far on the large scale CMB, the full sky data set. And yeah, and tell you a bit more about how we are able to using this PC principal component technique to compress all of that information that we have in this a very precise data set to get any constraint on to get a constraint on any ionization history between a certain range. And so that is in the form of this RELIKE code, and it really helped to simplify model testing. And I'll go into a bit of detail about that and help enable fast and consistent joint analysis in a way that was not possible before. So at the end, I will also briefly touch on some model-independent constraints on reionization that you're able to have from PCs, which I also find very interesting. Okay, so let's get started. A little bit of background on reionization. This is sort of the history of the universe diagram. We start with inflation over here, and there's the cosmic macro background that's emitted here when recombination happened, when the universe became neutral and transparent, and like a propagate straight toward us. And this is us astronomers looking back over here. There is all this galaxy and star formation going on, which we call the epoch of reionization, because they started emitting UV light and ionized the gas around them. So what happens is that you got the CMB photons coming all the way to us, traveling all the way to us since 380,000 years after the Big Bang. And they travel through this basically cloud of free electrons before arriving in our telescope, Planck staring back. So observing all of these photons, and these electrons have they scatter with the photons, so they leave particular signatures on the CMB observations that we can actually extract and use it to learn about reionization. This is not the only probe of reionization. There are also many other ones like quasar spectra, with which we understood that the universe was mostly ionized by around a shape of a 6. CMB anisotropy is only one of them. Galaxy luminosity functions and 21 centimeter experiments, and actually more than that, intensity mapping in general as well. So there are many probes of reionization. I will first focus on the CMB. CMB is just like any light. It has temperature and it has a polarization. So on every direction we look on the sky, the temperature actually fluctuates about a mean of 2.7 K, and we call that fluctuation temperature anisotropy. And so whenever we have a map, we can use our favorite tool to do a Fourier transform and to get a power spectrum. It's not exactly a Fourier transform, spherical harmonic transform on the spherical sky, but so it gives us the temperature power spectrum as a function of the angular wave number, or we call multiple L here. So this is the observable in the CMB. We also observe polarization, and we decompose that into E mode and B mode. E mode is a curl-free mode, and the B mode is a divergence-free mode. What is useful for reionization is going to be the E mode polarization. So here again, we use our favorite tool and get our E mode polarization power spectrum, which you see has acoustic wiggles in the spectrum, just like the temperature one. However, it also has this low L bump over here, which is really what induced by reionization. So we call it the reionization bump. So the effect of the reionization on the CMB power spectrum is, first of all, it suppresses anisotropy. So you can imagine as photons go through scatter with those free electrons on its way, over here it's going to scatter in random direction. So that suppresses the original anisotropies that we would have seen, both in the polarization and the temperature. And that's done by a factor of e to the minus 2 tau, where tau is defined as the optical depth. Compton scattering optical depth. So this is the important parameters, one of the 6 lambda CDM parameters that are being used to model the CMB in the most baseline model. It also creates polarization anisotropies on the large scales, as I just shown over here. So yeah, small angular wave number large scales is the left. In addition, it also induces a Sunyaev-Zadorowicz effect on the smaller scale, which is also a great way to probe the inhomogeneity of and duration of reionization, which I will not go into much detail over here. So we will focus on using this E mode polarization power spectrum and its signature to of reionization. All right. Yeah. So let me explain a little bit of how this works. Oh, by the way, yeah, feel free to interrupt me if there's any questions. Yeah, since yeah, just open your mic or something, since I probably won't be able to see all the hands raising if there is any. Yeah, but let me just explain real quick the physics of how this can arise. This is a picture borrowed from Reion's tutorials. So you can imagine, yeah, I used to do this in a live talk, which is much easier, just demonstrating with my hand. But I can try again, see if it works. Otherwise, default to the image. You know, so you can imagine that you are the audience. So on the other side of the computer, you're the audience. I am, you know, a free electron sitting here, and there is a photon coming from above and from my right hand side. So the photons coming from above will always have the polarization in the plane transverse to its direction of propagation. So its polarization is in this direction, in this plane. And after it scatters and goes toward you, which is the observer, into the screen, it only can have its polarization in the vertical plane. So, so the only polarization direction that is left, I used to like to do this, doesn't work so well on Zoom anymore. is basically going to be this horizontal direction. And similarly for the photons that comes from my right, has this polarization in this kind of vertical plane. And then so when it scatters and going toward you, it can only have the polarization in this vertical plane. And so the net is that you have only polarization in the vertical direction. And if you use the quadrupole in the anisotropy of the CMB, then which means, for example, it could be cooler from above, hotter from the right side. It's a quadrupole pattern. You end up with a total net linear polarization going toward the observer. So that is what we're observing on this bump over here, is the scattering with the temperature quadrupole creating extra polarization anisotropy as a result. And usually this is happening on the horizon scale, so which actually changes as a function of redshift. So as we go further back in time, we are actually looking at smaller and smaller scales. So over here would be higher redshift, and lower redshift would be the signature of on larger scale, smaller wavelength. So so therefore, this shape of the bump is telling us information about a particular history of reionization and how much scattering there has been. So we can use this, basically the height of this bump. So typically people use basically the height of this bump and the rough location to get the sense of where the average scattering happened. But there's much more information to that. We can analyze really the shape of this whole bump. So the simple approach has been to use a Tench function to parameterize the ionization fraction, which is the amount of free electrons to neutral hydrogen. And that is just evolving, pretty much zero the whole time, and suddenly you have an instantaneous reionization as Tench has a little width. And then it fully ionizes to about 1. There's a little extra than that because there's also helium that's being ionized once here and later. And if you plot the cumulative optical depth, it starts to climb pretty much steadily since this instantaneous transition redshift. So we propose to use the principal component method, which was first proposed by Hu and Holder in 2003. This is a much more flexible way of capturing the observable effects of any ionization history model on the data, on the CMB data. So it starts with a fiducial model, which we adopt to be basically a constant of 0.15 and 0 before some Zmax and fully ionized, just matching the Tench after redshift of 6, some Zmin. After we pick the fiducial model, we would perturb around the fiducial model in redshift to get a response in the E-mode polarization power spectrum. And to do this, you would basically have little triangles, almost delta functions in redshift, and looking at the derivative, the response in the CLE. And after you've done that, you can construct a matrix, a Fisher matrix of CLE with respect to these perturbations of the ionization fraction in different redshift bins. So you can use that to obtain the eigenfunctions of the Fisher matrix, so do a diagonalization. And after you end up with different modes in redshift space. And these are what we're gonna be called the principal components. So there's a sum over many principal components, with SA being the function itself and MA being its amplitude. We're not done yet. We can rank the PCs by their inverse variance. So the beautiful thing about this is that only the first few PCs are needed to completely describe the impact on the data. So here I plot the 5 PCs. You have, the first mode, which is almost just like an optical depth with a slightly higher weight toward the redshift. The second mode allows you to change high redshift versus low redshift ionization. And the other modes just starts to fluctuate more and more, looks sort of like a Fourier decomposition. And here we plot the optical depth, cumulative optical depth, and you can see over here is the total tau, total optical depth, and the first pieces leave the most observable, gives the most contribution to it, which makes sense because they should leave the most observable impact. Just want to show you a little demo of how that works. We have the Tench. This is a maximum likelihood model from a while ago, so no longer the best one, but just pick any model, and then you can do this decomposition, just sort of like a Fourier decomposition, and you can use 1 PC, 2 PC, 3 PC, 4 PC, and 5 PCs. So the thing is, we only need 5 actually to describe any cosmic microwave background data to cosmic precision, variance precision. So it's way enough for Planck. And of course, the number 5 is also tied to the particular redshift range that you're looking at. So between 6 and 30 is what we're doing right now in our fiducial analysis.
Can I interrupt and ask a question?
Yeah, please go ahead.
You want the I guess you want the reionization fraction to always be positive, right? But the PCs can be negative, so
yes.
So in principle, a free fit could maybe allow something unphysical. Do you control for that, or?
Yeah, so that's a great point. That's actually my one. Oh, did I not have that slide? Okay, so I will just tell you in person. This is a point I would like to make, as was going to make as well, that you actually do not want to use the PCs to reconstruct the ionization history. A lot of people make that mistake and they think they can do that, but that's not the best thing to do. The best thing is more like it's more a forward model for you to get to what the impact on the observable is. In particular, is exactly what you're seeing on this slide here, the CLEE, the E-mode polarization power spectrum. That Planck measures. So it's able to describe the effect, basically let you calculate CLEE exactly, meaning better than cosmic variance precision that we'll never be able to observe. But it is not meant to be used to reconstruct the ionization history. In fact, sorry, I had a plot but didn't show it. In fact, if you plot this 5 PC decomposition in the ionization history space, you will see that there are some wiggles that that ends up making your ionization history below 0, negative, which doesn't make sense, right? But the whole point is that regardless of that effect, we are more interested in modeling what the CLEE is, and it does that perfectly. Great. So you'll see why this is helpful. Basically, in this MCMC analysis, so typically we have our lambda CDM 5 parameters, and then we have a parameter basically corresponding to the time where in the Tench model, the instantaneous ionization would start to kick in, and that would be a 1-to-1 correspondence with the optical depth parameter that we care a lot about. And I should say also, yeah, for some more general background, that we obsess a lot about the optical depth in the CMB measurement, because this is actually going to be one of our dominant source of error in the future when we try to when we measure a neutrino mass, for example, from CMB lensing, because this impacts our errors on the primordial power spectrum amplitude, and also would have the other implications for dark energy measurements as well. So yeah, and of course the neutrino mass measurements will in the future will be able to tell us, help us distinguish between the virus hierarchy in neutrinos. So this is why we're really want to nail this number down and its error bar correctly. But however, with the Tench model, as I have shown you before, it is an assumption of one particular model. It could be a really, really good one, but it doesn't capture all of the other possibilities that are out there that we could see, say, from simulations. And so the PCs, what it does is that it's going to be able to represent any model that you have. So what we do is we just do a constraint on the PC amplitude themselves, the first 5 PC amplitude that I show here. And after that, what we get is basically constraints on every single one of them, which then we can use to obtain constraints on individual models that you may be interested in, which is going to be absolutely physical. And so, but before I just go there with the effective likelihood code, let me show you what this. Let's just take a little brief look at the constraint here. So we have the 5 principal components, and the boxes are denotes the box, the edge of the box edge of the physicality priors, which is enforcing 0 to xe to 1, xe to be bounded between 0 and roughly 1. So this prior is just projecting 0 and 1 onto the principal component. So what that does for you is that everything outside the box is going to be unphysical. Okay, so this is something you were something you were asking about. This is one step in how we deal with the physicality as well. But inside the box, this is a necessary but not sufficient condition. So inside the box, you have all of your physical models guaranteed, they're in there, but there will also be some unphysical model. Does that make sense? Yeah. So what happens? So when we do make this choice, then anytime you have a physical model, I'm guaranteed to have a constraint on it. But inside this, I also have some unphysical model, although I will show later that our model independent constraint on optical depth does not depend on this unphysical models. Okay, this is a bit of an evolution from 2015 Planck which is the red, to green, 2018, and then there was a new version that was released, newer likelihood with S-Rho2, better cleaning of systematics, that moved it to the blue. And you can see here the trajectory in black that I've shown here. It is basically all of the Tench models. Basically the Tench model I shown varying when it was step. And you see it's only a thin slice through this entire space of models we're able to constrain with Planck. So this shows again how it is useful to have something like this. Oh, okay. Yeah, so the main goal of this talk was to show you about, tell you about this effective likelihood code, which we have built together using these PC constraints. So if you're interested in doing model testing, this is how you would do it. You have a particular physical model of ionization xe of z on this redshift range. You would project that onto the PCs to get an amplitude, so you get 5 numbers. And what we do under the hood is that we have a kernel density estimate over the whole 1 million point PC chains that we have. So basically just smoothing around this particular point that you're requesting, so our chain may not fall on every single possible point. So we do a kernel density estimate to obtain the likelihood of this particular point. And we also have another mode, which is just using the Gaussian approximation using the covariance we get from the chain. And it's actually a really good approximation in the 2018 data set. It wasn't so good in the 2015 one. And after that, after you get the likelihood, it's very easy for you to get a posterior of the model, assuming you've got flat priors on the model parameters. It's really just the likelihood itself rescaled. So yeah, so this code is available on GitHub. Is also available with the pip installation. So we only support Python 3. So pip3 install RELIKE would get you the code. There is a simple notebook, Jupyter notebook tutorials on the GitHub. And you can also hook this code to the various different MCMC samplers. Currently, the Python package supports the Gaussian mode only, which should be sufficient for most models as we tested. But we also have a Fortran implementation of exactly the same algorithm in the Gaussian mode and in the KDE, the kernel density estimate mode as well, that we have hooked ourselves to Cosmo MC to produce the results that we showed in the paper. That we'll also show in a minute. So this is also available and online. So everything is over here in this code. Just want to show you a little bit of how it works. It's really easy. You import RELIKE. You can plot the PCs over here, and if you have defined a tench model, we actually have define any model. We actually have a in-house. We have a tench model built in already, and if you just have any ionization function, so this just let you get the ionization function version of 10 for tench model here. You just do a get pc.get mjs. You will give you the amplitude of the PCs that's printed out here. And with the Gaussian likelihood in RELIKE, you can do a get log like, giving it the mjs, and it'll give you the log likelihood. So it's very easy to pick a model and wanting to know how far are you from the Planck best fit model. This is already normalized to the best fit tench model in Planck. So typically what people do is that they will get the optical depth of their model, which could have very different shapes than the tench model, and compare that to the optical depth constraint from Planck, which is derived assuming the tench model. So it's sort of an inconsistency there. And what happens is that in the previous 2015 release, by doing this, you actually miss out on a lot of the high redshift ionization evidence that was in the data. So models like that would be ruled out too stringently. So we had done that analysis before, but it turns out a lot of those hints was actually coming from systematics in the 2015 data. But still, it shows how this is a much better way of much fair way of comparing different models. There still remains a high redshift component, no longer a 2 sigma evidence, but more of an upper limit, which I will also show very soon. This is just showing how you can only go from a few lines to a posterior plot of your ionization parameter, and here we show the tench model. Yeah. I believe I can probably go through this part fairly quickly. This is just showing some of the model testing that we've done with running an exact Planck likelihood with our own effective likelihood that is much faster. So for comparison, the exact one takes about 24 hours on a cluster of 8 cores, and the KDE and the Gaussian takes a few minutes on my own laptop. Actually, I think even less than that for this one parameter model. So this is showing how the posterior looks like. They totally match pretty well, and there's a cumulative optical depth plot as well showing how well it matched. So as you have remarked earlier, there is like some wiggles as well as a result of integrating this truncated expansion of the ionization history. Yeah. We'll also show a 2-step model. I think this is where, yeah, it only took a few minutes to get the results with our code. The tanh is pretty instantaneous. So yeah, this is the two-step model where we do have a high redshift ionization plateau, and then the transition that can happen at different redshift. So again, here if I plot out, the high redshift optical depth and the low redshift part of the optical depth, I get contours that are pretty much matching as well. So I would say we tested the code pretty well. Here the interesting thing is that we also looking at, so we called that two-parameter model a two-step model, and we look at the two-step model, which is the black here compared to the blue curve that is tanh. So you see there's a little shift in that optical depth to a little higher, and that is because of allowing this high redshift ionization. So there is, so again, using tau, using tanh doesn't fully capture everything, though this is a relatively much smaller shift compared to what we saw in 2015. Yeah, so we can also do a comparison with the model independent constraint. So these two are defining particular models, and now we're just looking at all the constraints the PC we're able to get. You see this red shaded plot over here, and that is very consistent with the two-step model plot. So from all of this, from the model independent constraint, we can derive an upper limit on the high redshift part between the 15 and 30. It's 0.02 at the 95% confidence limit. I'm showing in 2015 how what the cumulative plot contour looked like for tau, and in 2018, which is our latest constraint in pink over here, you see that this 2 sigma evidence at redshift of 15 has disappeared, and now we end up with the upper limit. What is interesting was that the Planck paper actually initially had using a different method called flex, not an upper limit of 0.007. I think with this paper and a different paper that also converged on saying that this is too low of a number, they ended up updating in the erratum just a month or two ago, that they have fixed some mistakes, and so they end up with 0.023. So now we're actually having consistent upper limit. Yeah, and we also validated our result before publishing it using a two-step, using our two-step model, basically also finding that without using anything PCs, this is just the exact Planck likelihood on the totally physical model. We get that the higher redshift part should have around the same upper limit on optical depth. So now we believe that we have converged on the truth. Hopefully. Okay, so I think I can probably move on to the next topic soon. Maybe just saying we also changed our Zmax assumptions and from 30 to 50, and checking the results are consistent, and also removing physical models actually, does not impact our result neither. Yeah, so I guess one more thing to highlight is that because it's so fast now to just give a Python code a function of ionization history and be able to get the Planck likelihood very quickly, this makes it so much easier to do a joint analysis with all these other data sets of reionization. Before, people just put a Planck tau prior on their data set, and it's probably okay for a lot of models, but it's misleading in some other ones, especially if you have higher reionization tail, as you would see in some simulations. Then that tau is derived tau prior is derived from the Tench model, and that would not be a consistent way of doing a joint analysis, but it was so much work to do it properly before. You have to modify CAM, you have to hook to the Planck likelihood data set. So it was so much work before, but now you simply need to plug in RELIKE as a Python module for your likelihood. Okay, I think that's all I have to say on this topic. Are there any questions before? So I was also planning to give an update, very quick update on SphereX as well, as some of you were interested in that. But before I move on, is there any questions on this part? Okay, so I suppose that's a no. So yeah, thanks a lot for listening. I'm gonna move on to the SphereX part again. Feel free to interrupt me anytime. I believe I have 10 more minutes or something like that. Is that right? Or 5 more minutes?
Yeah, I think we're gonna, well, the plan is to go to 12:30 with questions, so.
Oh, okay, okay. All right, okay, so I can go a little slower, I guess.
Yeah.
Okay, perfect. All right, so yeah, so SphereX, let me give you a bit of an update on SphereX. First of all, SphereX is a NASA medium class explorer mission. It will launch in 2024 and conduct over the course of 2 years 4 all-sky surveys. So it will basically every half a year will survey the whole sky. It's right now in the detailed design phase, and we passed the preliminary design review last year and going into the critical design review basically at the end of this month. So that is very exciting. And I believe Professor Will Percival was on the preliminary design review panel last year. So thank you so much for all of your feedback and hard work and helping us prepare to get to where we are right now. SphereX, I should at least read its long name over here, the Spectral Photometer for the History of the Universe, Epoch of Reionization, and ICES Explorer. So you probably have a sense of what's coming up and what kind of science we are actually doing. So yeah, so the science questions we're answering are threefold. First one is, how did the universe begin? So we're looking at inflationary physics by measuring the 3D distribution of galaxies. The second one, how did the galaxies begin? And we study the history of cosmic light production through the near infrared background fluctuations that SphereX will be able to observe. The third one is, what are the conditions for life outside the solar system? So we would survey the Milky Way for water and other biogenic molecules to study, ICES, which is often associated with the conditions with the life. Okay, yeah, so in particular, how we would do that? Well, we will build the first all-sky near-infrared spectral survey. A little bit of more information on the SphereX instrument. There we have a wide field of view, 3.5 degree times 11.3 degrees. So here's a comparison of SphereX field of view versus the WISE field of view. And each pixel is 6.2 arc-second on each side. The telescope effective aperture is 20 centimeters. So that's the inside blue over here. This is comparison with the WISE primary diameter. We use the linear variable filters. So this is a really cool technology that lets you basically have a cheap spectrum. We have, usually taking a spectrum of a galaxy is very expensive. I've stared at it for a long time, and then we have here. What we have is basically 102 very narrow bands. So it's like a photometric survey, but very narrow bands, and we got 102 of them. And the technology that enables us to do that is the linear variable filters. So how the linear variable filter works is that there are bandpass filters whose central wavelength is going to vary with the position. So the light that hits ends up falling on the particular position and that is the wavelength that is going to go through. It tells you which wavelength is going to go through. So what SpherX does is going to dither in space as it looks at, say, galaxies, and then let different wavelengths fall onto all of these elements to get the full range of the spectrum. Yeah, so basically we have an outsky survey with 102 fine photometric bands, and we end up having a spectrum literally for each 6 arcsecond pixel on the sky. And here's an example of what we can do with that. We can study galaxy spectrum. So here is an example spectrum of a passive galaxy at a lower redshift with 1.6 micron bump. Higher redshift start forming galaxies in the blue over here with H alpha, H beta, O3 emission lines. And so we're able to, compile basically hundreds of millions, a catalog with hundreds of millions of galaxies that we'll be able to use for our cosmological analysis using its 3D distribution to understand the beginning of the universe. And in particular, this is very useful for the reason why we need this, this fine being able to resolve those lines and bumps is so that we can have an accurate estimate of our redshift. So to be able to place the galaxies in 3D. Beside this, yeah, we think that this is going to be a really exciting data set for with a lot of discoveries. So the data is actually going to be all public, so for the community to go in and discover things themselves. I should also say there are the other two science goals. One of them is looking at the near infrared clustering power. So this is the background light from background light that goes through a lot of the history of the universe, and they're looking at the clustering power spectrum. This is an example. For the third goal of studying ISIS, this is going to be a background object inside of our own galaxy, inside Milky Way, as it travels through various kind of objects, clouds, planets. You'll see absorption features in different ISIS. So ISIS is not just H2O, water, there's also CO2, CO, etc. So these absorption lines will tell us about where these ice are, and so that one of the data product is to have a catalog of column densities toward different objects in the Milky Way. Okay, so yeah, so why is this useful for our science? Well, with the hundreds of millions of galaxies that we can observe and locate their redshift accurately, we are able to use that distribution to study something very important about inflation. I showed a picture earlier of the universe evolution. Inflation is at the very beginning where quantum fluctuations got stretched out to cosmological scales as the universe expanded very quickly within the first fraction of a second. And that process, we actually don't understand it as well. There are various different models of how that happened. Some of them involves a single field driving inflation. Some involved multiple different fields that are active during inflation. And so theorists have a very wild guesses about what can actually make it work, and we need data to be able to constrain that. And in fact, Planck has done this very well. So this is the Planck contour over here in the parameter space of the running of the spectral index. So basically, how the primordial power spectrum is tilting and tilting even more with different scales. So it's like a tilt over tilt, and then the primordial non-Gaussianity parameter, which I can just say very briefly that it characterizes deviation from Gaussian primordial fluctuations. So as you know, probably as the inflation as inflation stretched those quantum fluctuations to cosmological scales, these fluctuations were later seeded dark matter clustering and forming galaxies and all of us. And so understanding this nature of this primordial fluctuations is very important. And so far, you can see with Planck, we have roughly about an error bar of 5 on the how much this how much non-Gaussianity there is. But what is interesting is that once you start to shrink, if you can start shrinking the error bars like spherics will be able to do with its various power spectrum and bispectrum measurement, you'll be able to start distinguishing between single field and multi-field inflation. And so in particular, we do not expect FNL bigger than 1 with a single field inflation. So this is going to be really, really interesting and providing a definitive test of something important about inflation. Yeah, and to remark also that spherics will improve 10 times upon the original, the Planck, current Planck uncertainties on FNL and going down to sigma FNL of about 0.5. And to be able to do that, we need a very accurate modeling of power spectrum and bispectrum. And also we do this with a multi-tracer, so many different samples. So I'll be telling you a little bit more about the progress that we have made so far on these modelings and some of the challenges that are coming up. Okay, so this is basically give you a sense of the modeling that's going into the bispectrum, and this is not even complete. This is with a lot of assumptions like plane parallel. This is only perturbation theory to a second order, and we include the redshift space distortion. We include multi-tracer effects. We include primordial non-Gaussianity induced terms, which are labeled and circled below. We use a bivariate bias model to model the galaxies as biased tracers of the underlying dark matter density. So please by no means feel like you have to digest these equations. This is just to show that there are various FNL corrections to terms that are being induced, and in particular, there is a scale-dependent bias on the large scales that will show up. I should also define probably what the bispectrum is the 3-point correlation function in Fourier space, just like power spectrum is a 2-point. Yeah, so this is our tree-level linear modeling, and eventually we might extend the modeling, but so far some of our challenges is that we have a very huge data vector. We have 5 galaxy samples, which is a bunch of different, gives a different multi-tracer bispectrum, 11 redshift bins, and hundreds of triangle shapes, and also these triangles. So bispectrum allows you to have 3 legs in Fourier space that form a triangle. Each of this triangle has can have any orientation in the whole 4 pi steradians. So you could have up to hundreds of orientation bins. But if you go into the multiple space, actually, if you project this orientation, the 2 spherical at the angles that parameterizes the orientation of the triangle with a spherical harmonics projection, just like we were seeing earlier in the CMB decomposition, you can end up with just a few multiples that carry all of the information that you need. And in particular, we want to do a Fisher analysis to look at the different multiple configurations and find out that actually the even multiples and M of 0 capture most of the bispectrum constraints already. This is not entirely new. There's also another paper by Samusha and Gaglani that also have shown this for RST and BAO parameters, but we wanted to double check for FNL. This is a really preliminary plot. It doesn't have the full multi-tracer glory. This is the paper is still being developed, and this doesn't have all the nonlinear, all the bias term in it either. But I believe the result should be should not change too much depending on those things. So what we see here is that the FNL constraint is actually mostly captured in the monopole. So I should explain what this plot is. We're normalizing, we are basically comparing the improvement ratio of the uncertainty on FNL compared to the full bispectrum, which is over here. If we used only selected pairs of LMs for the bispectrum multiples, so blue is all of them for at L max of 4, you can see that it's pretty much, or even L max of 2, it's pretty much captures all of the information. This little bit is just integration error at the level of 10 to the minus 3. And if you choose m equals to 0, you get down to this green curve over here. So what this is saying is that I can actually ignore all the different orientation bins and only use one single multiple to be able to capture all of the information on my FNL. Of course, it remains to be decided if we want to go to higher L to be able to capture more information in the other cosmological parameters, but we could also decide to let the power spectrum carry us through with that. We also face various other challenges such as wide angle effect, which becomes very prominent on large scales. This is one thing that SpherX will really need to deal with because we're going to be the first one to cover such a large area of the sky in galaxy redshift surveys. We can no longer use. There are various effects that creeps in on such large scales that are no longer that we weren't forced to take. We didn't have to account for before. So, for example, the plane parallel assumption starts to break down. That is the one where we assume when we look at different galaxy pairs that the line of sight is parallel to each other, and that totally breaks down when you go to opposite side of the sky. So that doesn't work anymore. And one of the things that we're exploring right now is to use mixed plane expansion from the plane parallel approximation, following Castorina et al. And Beutler et al. We're looking at how that changes what's the effect for different redshift bins of SpherX. And here's a very preliminary plot again showing here on the red curve is for the low redshift, and these curves are for higher redshift. So showing that at the particular K, you have more wide angle effects that you need to deal with for the lower redshift. We also needed to come up with new ways of treating the window function, in particular the integral constraint, when you start having a scale-dependent bias that blows up some of your integrals that you try to model with. So we are actually adapting this to work for FNL modeling as well. There are also various GR effects that creeps in on the large scale. And finally, the spherical fluid basis spaces is something we're playing with as well, which is super interesting. It is the full, it is the eigenfunctions of the Laplacian on the full spherical 3D spherical sky. So you have spherical harmonics for the angular part and Bessel functions for the radial part, and they form a complete basis. And we're also looking at bispectrum and power spectrum in this basis. For the bispectrum, it turns out to be very challenging to even compute the theory model, to have a fast enough code to compute this theory model. But so far, we're working out the theory. This is led by a student, Joshua Benabu, who is now a graduate student at Berkeley, and in collaboration also with Isabel Sands and Henry Gebhardt, who is a postdoc at Caltech, and Olivier David, of course, who supervises the Cerex inflationary work. Yeah, so I guess this is everything I have. I guess I'm running out of time as well. Thank you so much for listening. This is a very short update on the Cerex part, but I'm very happy to talk to you more. I know there's a lot of expertise in the groups here as well on infrared surveys and large structure survey in general. So really happy to talk together and collaborate if you ever have any suggestions and ideas for how to move forward.
Okay, great. Thank you very much. That was a really nice talk. Are there questions? Yeah, Neil.
Yeah, hey Chen. Yeah, a very nice talk. I had a question, I guess, about this multi-tracer part that you just mentioned.
Okay.
Yeah. So my impression, of Cerex was that it's kind of like a low-resolution intensity map, right? Like in the sense that you're not really trying to identify galaxies or sources, but instead you're just, mapping the intensity in each channel. Is that right?
Yeah. So I think we actually so there's an intensity mapping part to it, and then there's also a part where we can identify we look at spectrum of galaxies, right? So we can identify the redshift of the galaxies, and then we're gonna we'll have different redshift bins, and then we'll also be able to classify the galaxies according to the estimated redshift accuracy.
Oh, okay.
Yeah, so we resolve individual we
great,
see individual galaxies. Yes, yes. So I think you may be referring more to like this part of the there are like three very different work that's ongoing. This one is looking at just background light, so that's like integrated everywhere and not necessarily like they need to probably do some component separations, but yeah, that part is a bit more integrated observation.
Oh, okay, I see. Okay, yeah. So I see. So above, you're saying that you're expecting like tens or hundreds of millions of galaxies,
Yes,
individually like cataloged and identified. I see.
exactly. Right.
Oh, that's great. Okay. What fraction of the sky do you guys plan to cover?
Basically everything except the galactic, like we have to mask our own galaxy. So roughly we expect like Planck like 75% after you take out the galaxy center.
Oh wow. Okay. Fantastic. So do you guys then, envision being able to measure like the dipole on the sky? I was just curious.
Oh, that's a really good question. Yeah, I think there are some thoughts about like how there's some discussion about like if we can start to measure like those more fundamental anisotropies behind all the ones we have to correct for. But yeah, we don't have that's a really interesting thought. Yeah, we could probably do something with it.
Okay, cool. All right, thanks.
Thank you. Yeah, let us know if you're interested in talking more about this. Working on something like that at some point. Any other questions?
So I have a question about, so I'm also wondering, what are your concerns about observational systematics or things like blending in terms of their effect on the power spectrum?
Yeah, unfortunately, we're not there yet. In the sense that the science is we're just starting to prepare for our pipeline, but we only have 3 years to go. So you're right; these are really important questions. I think for blending in particular, there is some criteria for how to treat that. Like there might be, yeah, I'm not super expert on that part, but I think I've heard our team talk about yeah, different algorithms, either for deblinding or for just labeling, flagging the sources that has a higher confidence or lower confidence, and uses like samples that are more qualified to do the cosmological analysis. Yeah, but that's something I should double check with our redshift estimate team. Systematics, there are systematics on the large scales, so that we didn't need to face before. So yes, that could come in with survey strategies, and in on the theory side, there's those JR effects that we need to start worrying about. So all of this is still under investigation at the moment.
Okay, great, thanks.
Yeah, but basically we probably have similar systematics to a lot of the surveys, ground surveys that we know now, like a spectroscopy survey like DESI, and then photometric survey as well. But there'll be new things because we're sort of in between. We're sort of like, we have some elements of the spectroscopic survey and some element of the photometric survey. Yeah, we might end up having some of both systematics I usually see on both sides. And yep. I see another hand raised in one. Is that right?
Yes. So hi, yeah, very nice talk. So just a simple question. So I was just wondering, like, if your guys are actually able to produce a 3D map of galaxies, I mean, can you, like, in principle, like, do more cosmology than inflation?
Yeah, definitely. So I think so. For example, we may be able to measure BAO. Like we can look at BAO as well. We go to pretty high redshift. I don't know if there are any particular forecast that has been done for these other science. I know that we are able to measure, I think, neutrino mass and neutrino and omega K curvature related parameters much better than current analysis as well. I think there's a forecast in 2015 I can point you to it that also shows exciting constraints for these other extended cosmology models.
Okay, yeah, thank you.
But I'm sure we will have many more things we could do. One thing actually, so Alex mentioned I worked on compensated isocurvature perturbations before. It turns out that has a very similar signature to FNL with the scale dependent bias. If it exists, they would come from curvaton models, which is another kind of inflation model where you have a spectator field, a curvaton, and they end up producing compensated isocurvature perturbations. So SpherX will be really good for constraining that as well, which is one of the last isocurvature perturbations that we haven't really put very stringent constraints on.
Yeah, thank you.
Yeah, I am sure there are a bunch of other things that I might be forgetting, or maybe you will discover. I think hard enough about.
Okay, are there any more questions? Not, then I think we should wrap up. So thank you very much. This was a really interesting talk on both topics, which was great. So thank you.
Thank you.